Hello. We are continuing our exploration of infinite series and their convergence or divergence. So we have a series of, pun intended, we have a whole bunch of different tests, depending on the different kinds of conditions that we're given, that will enable us to determine whether or not a summation is going to have a sum that is finite, or is it going to be infinity. This time we're going to look at the alternating series test, and before we do that, we have to understand what an alternating series is. First of all, we start with a p-series. A p-series is essentially where we fix an exponent, so we create a power function such as k squared, or k cubed, or k to the 1/3, or k to the negative 10. So p can be a fixed number, and then we're going to create a function and then add up together all the finite values. A specific kind of p-series is the harmonic series. The harmonic series is 1 over k, 1 over x, 1 over n, or k to the negative 1, and so forth. Harmonic series, and then we have this. Consider the expression where I let negative 1 to the k plus 1 exist. What happens to the value of negative 1 to the k plus 1 as I continue to raise the value of k? Well, it turns out that if k is an odd number, then we end up with an even power, and we end up with a positive 1. If k is an even number, we end up with an odd power and therefore a negative result. And then we go back to positive, back to negative, and so forth. So we're going to alternate between 1 and negative 1. Oftentimes you will see this term, and the exponent itself doesn't matter. This could be k minus 1, k plus 1. It's really just trying to determine if the first term is going to be negative or positive. If k starts at 1 and we want the first term to be positive, then we'll put in a k plus 1 or a k minus 1 so we can guarantee a positivity. And then every other term is going to end up being negative. So, seeing this little generator right here is a way to create what's called an alternating series. An alternating series essentially is going to have alternatingly positive, negative, and so forth, all the way to infinity. Before we go any further in exploration of harmonic series versus alternating series, I want to point out that you might see the cosine of kx used as an alternative instead of writing negative 1 to the k plus 1 power. The reason is because the cosine of x, I'm sorry, let me start over. Yeah, the cosine of, I was thinking out loud. I think this should have been k pi, not kx. That's what it should have been. So we'll just do it. Yeah. Just give me 1 second. There we go. Cosine of k pi, it would be used to alternate. So what I mean then is k is 1, then we have the cosine of pi. The cosine of pi is negative 1. If k is 2, we have the cosine of 2 pi. The cosine of 2 pi is positive 1. Cosine of 3 pi is negative 1. Cosine of 4 pi is positive 1, and so forth. So the cosine has that nice effect of cleanly alternating between 1 and negative 1. So this is another way. If you see this, be careful and like, don't confuse the x with the pi like I did. But if we see multiples of pi inside a cosine, that's a surefire way to alternate between 1 and negative 1. So now what we've done is we've defined the difference between a regular series and an alternating series. To be an alternating series, we just have to oscillate between positive and negative terms being added. It's a fascinating outcome related to alternating series. And the question starts with, does my alternating harmonic series converge or not? So again, it's called an alternating harmonic series. We're going to use the alternating series test. Here's the way the alternating series test works. Suppose you're taking the sum of a sequence, all the terms of a sequence, all the way up to infinity. Then, if we can say that every consecutive term is going to be less than the term before it, every term in the sequence will be less than the term before it. Now, there's a little caveat in there. It says for sufficiently large k. What that means is we don't always have to have the next consecutive term being less than the term before it. But if k is large enough, it should then become always true. So this is a way around certain conditions where the functions start off not greater or less than the other, but eventually becomes that way. Notice, by the way, the absolute values here. I'm not talking about whether they're positive or negative. We're just talking about the actual value of the terms. So basically what that means is that the absolute value of the terms in the sequence must decrease. This is a fancy way of saying that. Also, if we take the limit of the absolute value of the sequence as k approaches infinity and that equals 0, then we can say that the series converges. So essentially 3 things need to be in place. We need to have an alternating series. The absolute value of the terms in the series should decrease over time, and as we allow the sequence to approach infinity terms, the sequence itself should converge on 0. If that's the case, then the series will also converge. It's a really simple test here, so all we have to do is show that u sub k absolute value is going to be bigger than u sub k plus 1. So here's u sub k, here's u sub k plus 1, pop them in there, and we can say since k plus 1 is always larger than k, when k is positive, obviously, and we know this is true for all k larger than 1, then the reciprocals are going to reverse our inequality. In other words, if k plus 1 is bigger than k, then 1 divided by k plus 1 will be smaller than 1 divided by k for all k values bigger than 1. So we passed the first part of the test, that is to say the absolute values of the terms are in fact decreasing. Second part of the test then is if we allow k to approach infinity, do we get 0? And the answer to that question is an obvious yes. Therefore, we can say that the alternating harmonic series in this case, does in fact converge. Something a little bit more interesting, maybe, I don't know. We have negative 1 to the n over the natural log of n. First thing I do is I find the absolute value of u sub k, which is 1 over the natural log of k. Absolute value of u sub k plus 1 is the 1 over the natural log of k plus 1. Notice as far as absolute values are concerned, I don't really concern myself with this negative 1 to the n power because I'm going to take the absolute value. I'm going to get positive results anyway. So this is either going to be 1 or negative 1. Results are going to be 1 no matter what. So clearly, since natural log of k plus 1 is bigger than natural log of k, for all k is bigger than 2, then 1 over that natural log of k plus 1 is going to be less than 1 over natural log of k. Carrying on then, we've got the limit as k approaches infinity of 1 over natural log of k equals 0. That's something that we don't have to get all fancy with. We just know that the natural log of k increases without bound, therefore the reciprocal of the natural log of k will approach 0. It's one of those standard things. So the alternating series converges. Just to be sure about this, I took the exact series as shown and put it into Wolfram, and the Wolfram said convergence tests. It even named the test, the alternating series test, the series converges. And so there's the evidence to support my conclusion. Now, there's one other thing that you'll be asked to think about and to do when it comes to alternating series, and that is find the error of an estimate. First of all, what you see here is a series of partial sums for this specific alternating series. First, we have the alternating because of the negative 1, positive 1 situation, and second of all, we have the series is going to decrease because the denominator is going to keep increasing. So the sequence is going to decrease. Now, if you look at this, again, this is a sequence of partial sums. So the first partial sum is really the same as u sub 1, which is the first term. And the first term in the series is going to be 5. The second term in the series is going to be 5 minus the second term in the sequence, which is 2.5. So the partial sum is here, and it goes all the way down to 2.5. And then when I add the next term, it's going to be above, because we're going to add 1 over 0.6, and then we're going to subtract and add and subtract and add and subtract and add. And the whole time we are converging on what is the actual absolute sum. Now we may not be able to find the actual sum without using Wolfram Alpha or some other fancy technology as a high school student. However, we can predict the accuracy of a partial sum approximation. In other words, if I add up sorry about that. If I add up the first 10, 100, 1,000 terms, if I add up the first 1,000 terms, how close will I be to the actual sum? So to explain this a little bit more, we're going to look at a little shortcut to answer that question. And so just bear with me here as I point out some logical statements. First of all, for any partial sum, S sub n, the distance from the partial sum to the actual sum will always be less than the distance of the partial sum to the next consecutive partial sum. Here's the way it looks in math. The nth partial sum less the next partial sum. If I take the absolute value of that, it's always going to be bigger than the difference between the nth partial sum and the actual sum. And so what, you say? Well, here's the thing. If the difference between the actual sum and the nth sum is less than the difference between the n plus 1, or two consecutive sums, and we learned in an earlier video that the difference between two consecutive sums is always going to be the last term in the series, here we can now say that this u sub n plus 1 is going to represent how far off s sub n is from the actual sum s. Now that's a lot to chew on, so first thing I'm going to do is go back to the initial supposition that the distance from any partial sum to the actual sum is always going to be less than the distance from any partial sum to the next consecutive partial sum. Since the distance between consecutive partial sums is always the last term in the series, we can use the last term in the series to estimate our error from the actual sum. Let me point out one other idea before I show you an example. Notice that this statement is true whether our first partial sum is above or below the actual sum. It doesn't matter, because we're using absolute values here, we're talking about distance. Here we can see that this partial sum is closer to the actual sum than the distance between the partial sum and the next consecutive partial sum. So the blue line is shorter than the green line, and this will be true no matter where I start my partial sums. Once again, that enables us to say this right here, which is the difference between my estimate and the actual sum. So this is how far apart my actual sum is to the estimate. Is always going to be less than the last term in the sequence plus 1. So if we want an estimate of the error, all we have to do is find the last term in the sequence, and we know that the error is going to be much smaller than that. Here's what I mean. Observe that I used Wolfram Alpha to estimate the actual sum to infinity of this particular series at 3.466. So that's the actual sum. In most cases we won't know the actual sum, but in this case that's what it is. So the next thing I could do here is find the partial sum. So this is the sum of the first 10 terms of the sequence, and that turns out to be about 3.22817 or so. That's the partial sum, s sub 10. Now according to Wolfram, the infinite sum is actually around 3.46574. So to estimate how far off the partial sum is to the actual sum, if I'm going to the partial sum s sub 10, then I will find u sub 11, that is the 11th term in the sequence. U sub 11 turns out to be about 0.4545. Now, this is something we won't be able to do, but I can calculate the actual area. The actual error, is only about 0.1184. But what I know from my conclusion based off of u sub 11 is the actual sum, the actual sum to infinity cannot be 0.4545 more than my estimated sum. That is to say, I've just found the upper bound error by using u sub 11 as an estimate of the error in the sum. Kind of confusing, but here, I'll phrase it this way. Find the upper bound in the error and taking the first 200 terms as an approximation of the actual sum. So, to find u sub, let me start over. I'm simply going to find u sub 201, which when evaluated into my expression, gives me 0.0249. Therefore, the partial sum of the first 200 terms, aka s sub 200, is going to be no more than 0.0249 more than the actual sum. Remember the 200th partial sum. So if we go back, if I add the first 10 terms of this particular series, I'm going to be off by as much as 50 or 45%. It's a lot. Or not percent, I'm sorry. Just off by about a half a number. If I add up 200 terms to get my partial sum, I will be off by only 2/100ths of a unit. So depending on how accurate you want to be, you may not need the total actual sum. You can just add up the first finite number of terms and you will know how close you will be to the actual sum. I hope that makes sense. It's really hard to explain, but it's easier to understand. So spend some time again, pause the video, absorb it, but thank you for watching.